After a nuts talk, I'm not going to try to make jokes or anecdotes. I cannot compete, that's clear. I even had the problem when I'm supposed to speak in a conference like this. On one hand, I'm supposed to speak on something that connected to Avi, but on the other hand, I can only speak about my own research, which in the last 20 years has been a completely different area. And most speakers here didn't have this problem because whatever you do, Avi probably did it, whether you did expanders or lower bounds or randomness or whatever. So that was very easy for most people. I had more of a problem. But luckily, I can talk about one of Avi's favorite topics to speak about, even though he doesn't do actual research. And about 12 years ago, Avi gave a sequence of talks everywhere, sometimes called Depth Through Breadth, or Why We Should Go to Other Talks, where he advocated basically the general idea that it's good that theoretical computer science is this wide thing, and we can learn from many different areas about other areas within computer science and within other areas outside of computer science. So the truth is that this is not such a trivial thing, and I think it's especially true for Avi, because one of his real secrets of success is that he's really able to find intuitions and ideas and apply them in extremely different places from where they started. And this is really a unique strength that I'm trying all the time to learn from him. I still remember some of the first times that I met him, I would ask him a question, and he would say, oh, the answer is in that paper. And that paper is a paper that I knew very well already, but I had no idea that the answer to my question was in that paper. And somehow Avi was one who actually understood that you could apply things way, way more broadly than where they appeared. So, one of the names that this goes by is lens of computation of sciences, if you want to apply things from theoretical computer science to other sciences. I think that yesterday Avi talked about it in a more blunt way. He said we should be imperialistic as theoretical computer scientists. And I would like to show my part of this imperialism here. So I'm going to talk about complexity in economics. And the general idea, I'll show you a problem that would seem hopefully completely foreign to most of you because it's going to be something that makes sense from economic point of view, but not from any complexity point of view. But the approach that I bring to it, because of my background in complexity, everything except the question, the answer should look very familiar, the type of analysis, type of questions, and maybe even I will hint a little bit about the types of techniques used in the results. So this is what I basically want to do. And, classical economics talks about, a buyer and a seller trying to sell. Alice is trying to sell the tomato to Bob, and, there are demand curves and supply curves and so on. And that's a natural question. And, of course, once you have a bunch of items that you're trying to sell, or a bunch of buyers, or a bunch of sellers, or something of many, then you start getting into complexity kind of questions. And these are the kind of questions that are interesting in this new area of internet. And these are the kind of questions where we as computer scientists, as theoretical computer science, can start actually contributing. And so it's not as simple as I said, once you have many items and it's a complexity. Really, you want the complexity to really come from some combinatorial sophistication. So maybe if you look at it from an optimization perspective, the difficult thing is when you have lots of local minima or something like that. And this is really just show that there is some combinatorial sophistication there, that complexity is of the essence. So these are the kind of things that I want to talk about. And of course, the applications are everywhere. So this is not just so one of the dangers when you start from complexity and try to apply it to another field, whether it's biology or economics or physics or whatever, that you try to find, if you only have a hammer, you're trying to find a nail. So we'd better be certain that these are really nails over there. And there are really many applications where you can see this combinatorial sophistication really is a major problem. So the ad auctions, search ad auctions on the internet are a famous example. Spectrum auctions, where you try to sell rights to spectrum, to radiomagnetic spectrum. And there are many different bands and many different licenses, and there are complex interactions between them, is another famous example. Or even if you just try to allocate resources on the cloud, like basically memory or CPUs and so on. There are lots of interactions between them, and to understand how to do the allocation correctly and the pricing correctly, basically the combinatorial sophistication is your problem there, and the complexity is your problem there. So I'm going to try to focus on the simplest setting, where you can actually see the complexity biting you strongly, where you need to handle it. And this is the seller. This is the setting that I want to talk about that I've been looking at in the last few years. So Alice is trying to sell a bunch of items to Bob. And Bob has a certain value, a number, that he's willing to pay for each one of the items. And there's no sophistication in what happens when he gets a subset of the items, but rather it's just additive. So if his value for the cucumber is 7 and for the tomato is 8, his value for getting both of them is just 15. Now, the point is, and the question we're going to ask is the economics question. How can Alice, who's selling stuff to Bob, how can Alice make as much money as she can? Now, if she knew Bob's value for each one of the items, it would be very simple. If she knew Bob is willing to pay 7 for the tomato, she'd tell him, give me 7 and take the tomato, and he'd say, okay. And then she'd, of course, make, if she sells each one of the items with the amount that Bob is willing to pay, the maximum amount that Bob is willing to pay, of course, she makes the most money that's possible. But she doesn't know that. That's the private information that Bob has. Instead, what she does know, she has some kind of knowledge, partial knowledge about what could be his value, and that's captured by a distribution. So there is a distribution Fi and the possible values. You can look at it in two basically equivalent ways. One of them is that she already had lots of statistical tests and lots of surveys about many different Bobs, and she knows the distribution. And then she's using that information to actually now take money from Bob. Equivalently, really, that this is whatever she knows, wherever it came from, that's captured by a distribution, and now she, according to her knowledge, she wants to optimize the money she can take from Bob.
It's not a joint distribution.
No, and it's not a joint distribution, so again, I'm trying to make everything as simple as possible. Each one of these items, the value comes independently from a distribution. And the distributions are what Alice knows, but she does not know the value, and that's a problem here. Trying to, yes?
So the buyer will buy everything priced below its value? Because it's like an unlimited value?
Yeah, if what Alice gives him is the option, you can buy this for $7, then he will say yes or no according to whether his value is above that or below that. And we can say that if his value is exactly 7, he'll say, okay, I'm taking it. Okay? But maybe she can offer other things. Okay, and so that's the basic question. So again, I'm making everything as simple as possible. So there's no risk kind of thing. Everybody's only interested in expected values, both the seller and the buyer. And everything is independent to make everything as simple as possible. So let's start thinking first about a single item, and let's see what the classic economic point of view would be if you sell a single item. So now the buyer has a single value B, V, distributed according to some distribution F. The seller, who knows the distribution but not the value, wants to maximize her revenue. So what can she do? Well, if she sells at a certain price P, Bob will decide to buy it only if his value is above P, which means that their expected revenue would be the price times the probabilities that Bob buys. And now you have a nice expression, and you maximize that. And if you're an economist, you do first-order conditions. You can differentiate that if the function f, if distribution f is nice enough. And that's what the economist will do. This is called the monopolist price, and this is what you do. Okay, so this is classical economics. This is actually intro to economics 101. So this is very nice, but now here's a complexity, the computer scientist speaking. Is this the best way? So this is a computer scientist, really an economist, but this is a computer scientist point of view. Is that the best way to sell? So for example, we can think about general protocols between a buyer and a seller. They speak to each other a bunch, and then there's some kind of outcome. These protocols can be interactive, there can be randomization, and so on. So are there better ways to sell than just putting a price P and finding the best price P? Okay? So now you need to formalize this kind of, what is this kind of protocol? These are not the usual types of, entities in a protocol that we consider in computer science, but rather here the buyer has a private value V, has this V which is secret, and the way it's governed is not just going to play along with the protocol, whatever the protocols tell him to do, but he's not going to be some kind of adversary like we do in cryptography. The buyer is very simple, he's just trying to optimize his utility. Okay, so that's what he's going to do, and that's a rational model, and we can formalize that completely. And we don't need to completely formalize it because intuitively, what you think intuitively is the right thing. Whatever he can do to get the best, the lowest price basically, as long as it's less than his value, that's what he would do. And now you have a protocol, and the question is, among all protocols, including randomization, what's the best way to sell? Are there other ways to sell than just putting a price? And so Meyerson in the 80s, I believe, or maybe 70s, actually got a Nobel Prize for analyzing this question and understanding what's going on. And the kind of analysis that he has the following part. First of all, yes, that's not the only way to sell to put a price. There are other clever protocols. Second of all, here's a canonical way of all the protocols that are going to be completely equivalent to the following thing. Basically, what the seller can do is offer what's called a menu. If you want to get the item with a certain probability P, you need to pay this amount. If you want another probability, you need to pay that amount. So the original thing was if you want to get the item with probability 1, you have to pay 7. But now he can also allow you can either pay 7 and get the item with probability 1, or pay 3 and get the problem with probability 1/2. That's another protocol. And every protocol that you have, whatever as much interaction as you have, can be directly translated into this canonical form. So until now, this is just understanding basically the setting, and if you go home and try to formalize things, within an hour you should be able to prove what I've said so far. But then came a really interesting and mathematically sophisticated, non-trivial theorem that Meyerson showed, that if you want to look at the one that maximizes revenue, so the answer to our question is still one of the simple algorithms that we previously had. So you don't need to have a complex thing with lots of menus and lots of possibilities and probabilities and prices, but you just need to find the correct price to sell it. And that correct price is exactly the one that we saw in the last slide of trying to find the maximum P. And that actually maximizes revenue among all protocols. And that you can generalize to if you have actions between different players and so on. So this is quite a general kind of understanding. So the outcome from this line of work in economic theory is, yeah, if you want to maximize revenue, simple auctions are the best thing. For one item. For one item. And that's an important kind of thing. Now let's see what happens when we try to complicate things even a bit and talk about two items. So now we have a buyer, one seller, one buyer as before. Two items, V and U, values of the buyer for the two items, V and U, are distributed according to two different distributions, F and G, which we, again, for simplicity, let's assume they're even completely independent. And again, if you get both of them, the value is just the sum of V plus U. And the question is, what's the best way to sell it? So obvious, like in all direct sum problems, it's obviously that the best you can do is sell each one of them separately. Because, the values are independent, the distributions are, nothing. And the question is, that's the case. So I want to show that that is not the case, and let's try a very simple example. Suppose that, the value for each one of the items, so I have a cucumber and tomato, and my value for it is 50% 1 and 50% 2 for each one of them. What can you do if you sell a single item? Well, basically, there are two prices you can think about. Either you sell it for 1, in which case the buyer will certainly buy, and you'd get a revenue of 1 times 1, which is 1 in expectation. Or you can ask for a price of 2. And since with only 50% probability the buyer is willing to buy at value 2, again, your expected value will be 2 times 1/2, which is 1. So the best you can make for selling a single item is 1. And it would seem that the best way you can sell both of them is sell each one of them for one of these two prices and make 2. But here's a better way to sell. And the question is, what happens if the way that the seller sells the item said you can get only the cucumber and tomato together, but that's going to cost you 3? So there's no way to buy just one of them. I'm bundling them together. And of course, we know that lots of companies do tricks like that, right? So, and then what happens? What is the probability that the buyer will buy? He will buy if the sum of the cucumber plus tomato is more than 3, or is at least 3, which happens as long as not both of them are 1. As not both values are 1, which means probability 3/4, and he makes 2.25, that is more than selling these two things separately. Okay? So this is one of the, a computer scientist is already used to all this direct sum not working as expected. And the question is, okay, so how complicated can we handle this kind of thing? And it turns out that it is very complicated. There is an enormous richness of kind of optimal protocols. So it's not true that you always want to sell together. If the values were 0, 1, it's better to sell separately. If the values were third, 0, 1, or 2, then it turns out that the best way is a more complex thing, that you sell one item for $2, but you give a discount for both of them at 3. This is not just with this like pointwise distributions, but even if you have, let's say, IID on the range 0, 1, again, you want to sell a single item for X or both of them for a discount price of Y, but to figure out X and Y is like a 6-page paper. And then things become even more bizarre. So if you have two items, one of them is uniform 1, 2, and the other uniform 1, 3, then the best thing you need to use randomness. So no deterministic auction could get the optimal revenue, but the best way is to sell them is you offer you offer the first item and the 50% probability of winning the second item, and that's going to cost $2.5. Or you can always get both of them for $4. And that's the best thing that you can do. And no deterministic auction can get you as much revenue as that. And in fact, for more bizarre distributions, or there is a distribution called beta apparently, and if the two items are coming from these two distributions, there are infinitely many, in order to get the optimal revenue, you have to offer infinitely many combinations of probability price for the authors. And in general, it's still not understood how to solve these kind of things, but it is completely understood that the optimal auction is going to be a complex beast, as opposed to the single item case where it's a very simple thing, just offer the price, just say find the optimal price. So we know that optimal multi-item auctions are going to be complex, they may need to be randomized, infinite size even. They have this weird non-monotonicity in the following thing. Suppose that you have two distributions, then you take and increase one of them. So one of the players, you increase his value in each one of the possible states of the world. You would expect that you should be able to get more revenue from him, but that's not always the case. There are examples where even though you start with a certain amount of, with certain distributions, you increase the prices in each of them, and the revenue that you can extract goes down, surprisingly enough. And if you look at it from a computational point of view, figuring out what's going on there, suppose if you have n items, try to even figure out the revenue, the optimal revenue, or what is the optimal auction is like already very hard computationally. But I'm not going to go into the direction of computation. Yes?
Is the direct sum approach an approximation for?
That's an excellent question. I would bet you're a theoretical computer scientist. So, okay, but of course we don't like complex anything, because complex anything is difficult for the participants to analyze, to implement. So we would like to do a simple thing. I mean, as computer scientists, we're used that nothing that we want to do we can do, and we try to see how can we get over it? Can we do something in polynomial times that is an approximation, almost good, sometimes good, and so on. So of course, because we do not like anything complicated and anything complex, the question obviously would be, how much do we lose if we actually stick to simple auctions? And this is the type of question that does not come naturally to an economist, because they try to optimize things and find the best answer. And we computer scientists are so used to giving up and not succeeding in anything we try to do that this is our life, trying to see what we can do instead. So there are many different notions of simplicity here. So you may just talk about selling items separately and so on, not doing any complicated things. Or you may try to get a little more complicated. Maybe you just want to consider, let's not use randomization, which is terrible, and just stick to deterministic selling schemes. Or you can try to actually quantify things as you would do if you are a real complexity series. Let's try to quantify things, and then we can talk about how do you quantify how complicated an auction is. So one of the simplest way you can think of is how many different possibilities you offer to the buyer. How many menu entries, if we said there's this canonical form of just offering a price and the probabilities, then how many of possibilities are you offering to the seller? That could be like some kind of quantitative measure of a complexity of an auction. So I would like to talk a little bit about a qualitative measure and a little bit about a quantitative measure and see how we go according to time. So back to the questions that we had from the audience. Here's one theorem, that if you try to just sell two items separately, so don't do anything funky, just try to sell each one of the two items in the best possible way separately, which would be a deterministic, simple thing, just offers the best price, you get a two approximation. Okay? So I want to say just a few words about the way the proof goes without actually proving it. So this is a delicate thing. Can I say something useful about a proof without actually proving? I will try and we'll see how that goes. So, you have this direct something. So what I have here is a picture of the value of the first item versus the value of the second item. And you can imagine that within each point, each cell on the board is how much money am I going to make them from the optimal auction. So when we're starting with an optimal auction for two items, which exist, whatever it is, and everywhere in this little matrix, I'm just writing how much money am I making there. And then what would be the direct, so this is like a direct sum question. What would be the natural thing to do? Well, you fix one of the item's value and you try to look basically according to this line. So I fix a certain value of V and I try to look over all the values of the other player, and that sort of induces a different auction for one item. And somehow you want to say some things about this auction, how it's connected to the revenue of the first one. So that almost works. So basically it is true that apart from the V that I'm fixing, we get an auction for the second item. So the revenue that I get from that line would be the revenue for just selling a single item. And of course we have this V on the side, which is a loss there. So if you try to actually formalize what would you get by just doing the direct sum kind of approach, you basically get that the revenue of getting both items from both items is at most the revenue of the U item plus the expected value of the V item. And that's exactly the problem, because we want to replace the expected value of the V item by the revenue you can get from it. And that's difficult, and that's what we don't know how to do. The way to do that, though, if we split the space into two different parts, one of them where U is smaller than V, and one of them is when U is larger than V, then it turns out that you can replace the expected value of the small item is always bounded from above by the revenue that you can get from the larger item. And that would give you an approximation result. So the trick you need to do beyond actually just fixing one of them, looking at the other, is split the space in a way that allows you to bound the expected value of the small item. By the way, it's still open. Yes?
So when you explain that you can get, there is no direct sum and you can get more than the sum of the two in a combined auction, is it known whether there's a ratio bounding how much more you can get for selling two items together as opposed to doing each?
Yes, so this proof shows that you can get at most twice more. There is a lower bound that you can get at least 30-something% more. And it's completely open between 30-something and 100% more.
Before this result, it was not known that
No, it was not known that it's bounded. It's not known that it's bounded. It's not trivial to see that it's bounded. And again, the exact number is still unknown. And now what happens when you have a bunch of items? So two items, just to whet our appetite. What happens when you have n items? Then we know that it goes logarithmically. So you may lose a logarithmic factor. If you're selling n items, you may lose a logarithmic factor relative to if you sell them separately rather than as a bundle, but not more than that. That's if you just do the previous thing and do the correct recursion, that's what you get. And it's known that if you just look at the best of selling better, either selling everything together as a single bundle or selling each one separately, you get a constant factor approximation. And again, a constant factor of 1/6 sounds very good in this audience. For economists, it does not sound as good, but That's what you get.
But no, what's known about how good the 6 is?
It's not known. So again, I think it's known that it has to be at least 1/2. So you lose 50%, I believe. That's known. And there's a gap. Okay, so now I'm going to the second part. I'm trying to talk about a quantitative measure of how complex an auction is. So we want a complexity kind of result. So first of all, let's talk again about what is this complexity measure that I'm talking about. This is like the simplest choice you can make. There are, of course, other choices of complexity you can think of, definitely including computational complexity. But the simplest one is, remember that the canonical representation of any auction is basically you get a list of menu entries, each one of them saying, well, you can get 30% probability at winning the first item and 60% of the second item, and that would cost you $10. And you get a bunch of options like that. And of course, the buyer will can choose the best one of that. And that's what he does according to his certain values. And the complexity of an auction is basically the number of entries where I'm not counting and I'm always assuming that you can pay nothing and get nothing. Yes? Yeah, so we have only 2 items here. And because we said that the buyer is additive, so if he gets 2 items, he doesn't care if he gets them together or not together, I don't need to have a third row, what is the probability if you win both item 1 and item 2? It's just going to be the sum, and so we don't care about the third item. Okay. So the kind of question you would ask as a complexity theorist would be, okay, so how does a trade-off between the complexity of an auction and between how good it is, what does it look like? You would want to find some kind of curve, basically, and understand exactly the complexity revenue trade-off. So what would we have on the axis? So here are some natural points on the axis. About menu size, well, we have infinite menus. That's something. We have finite menus. And then we also have, finite that we understand, exponential size menu, polynomial size menus, and constant size menus. Now, polynomial size menus, by the way, is an auction that has a polynomial size description. Exponential size menus are also interesting because the log of the menu size is essentially the communication complexity of the auction. Because if you have a certain amount of possibilities, and me as a buyer, I have to tell to the seller which one I'm choosing, that's basically log of the menu size. So exponential menu size is really polynomial communication. Yes?
What's the parameter? Polynomial and what?
Okay. So basically, it's going to be in the number of items. That's the main thing. Okay? And the revenue, well, you can get some polynomial fraction, non-negligible revenue. You can get constant revenue. You can get almost everything. And then there's a difference between, fully polynomial time and polynomial time, fully polynomial time approximation and polynomial time approximation. So can I only get 1 minus a constant, or really 1 minus polynomial and a constant? And then I can get everything. So that's the kind of graph you would like to know, and here's what's known. So the red things, the full circles are what can be done, and the empty circles are what we know that cannot be done. Okay? So basically, we do have this nice increasing graph, and let's look at different parts of it and talk about them. Okay, so for example, let's look at the empty circle on the top, which is saying that finite menu size cannot give you everything. That's already what we said, that sometimes you need infinite menu size. If we look at the bottom, saying that if you have menu size of 1, if you just have one single possibility to offer, we said that one of the results that I mentioned was that you can only get 1/n fraction if you just send a single bundle, which turns out to be the best thing that you can. So that's the kind of thing. So I want to talk a little bit about the other points on this graph and what does it, how do we get them, the kind of analysis that we have. So let me talk about the 2 positive results. That with exponential size menus, that is with polynomial size communication, you can get as close as you want to optimal revenue, but not quite to optimal. Okay? And which also implies that with finite, you can get as close as you want to 1. So what would be the idea there? So in order to prove such a theorem, what do you need to do? You need to find how to take an optimal auction that we don't understand, because we said that we don't understand optimal auctions, and try to make it simpler, basically put it down to exponential size without losing too much revenue, but also only 1 minus poly revenue. And this is the way you basically do it, and this is basically the theorem that you have, that you can always find an exponential complexity, so exponential and n in the parameter and the approximation parameters that you want, such that with that complexity you could get 1 minus epsilon fraction of the optimal revenue. So basically I need to show how to convert an arbitrary auction into one that we don't know, that's not too complicated. And the way we do that is basically like a lot of positive results in this vein. It comes to a paper by Li and Yao, and this is the same Yao that we know from complexity, that basically says, well, really what happens, two different things happen at the low and the regular values, and it's extreme rare high value items that happen with very low probability. And the usual name for that is the core is where the values are reasonable, and the tail where the values where things happen, the very high values that happen with very low probability. And the nice thing is that because the two items values are independent, and now I'm using very strongly the independence assumption, it's almost impossible, and basically you get tiny little amount of revenue from the case that both of them are very high. So you could ignore the possibility that both values are very, very high. And now within the two other types of situations, basically go the following thing. Within the core, the usual kind of things, you basically do an epsilon net kind of thing. That's what you would expect. Only here you have a tiny little complication that changing things by epsilon may change completely the way the buyer behaves. So you need to do what we call a nudge and make sure that the buyer always moves in the direction that you want rather than the direction you don't want. So that's a little thing you need to do with the epsilon net. In the high values, basically, then you need to use the classical economic result saying that for basically in the high values, one of the items is going to be big and the other is going to be tiny, insignificant. So you can ignore the tiny one and basically reduce yourself to the situation of a single item, which economists know how to do simply. Okay, so that's a basic kind of analysis. That analysis turns out to be complicated, but the idea is here. Let me say, why can't you do such a thing in polynomial size? So why wouldn't you be able to get into 1 minus 1 over poly, let's say, with a really small, reasonable menu? So again, now we're looking for a lower bound kind of result. And we need to show that if you start with something in auction that has a small menu, it must lose a non-negligible amount of revenue. So the theorem says that even if you look at the very simple distribution on the hypercube, where the value for each item is either 0 or 1, you're not going to lose at least 1 over n revenue relative to the optimal thing, which is n over 2, right? So the expected value of the things is n over 2. You could sell the whole bundle for n over 2 minus about square root of n, because with very high probability the revenue would be square root of n low. The sum would be very close to n over 2, up to a square root of n. And then the buyer would certainly buy, almost certainly buy, and you'd get n over 2 minus square root of n revenue. So you lose square root of n out of the n revenue, and basically that is unavoidable if you have a polynomial size menu. So what kind of argumentation would you need for that? So basically you analyze the menu, and what would we do? So we have a polynomial size menu, but we have an exponential size of possible sets of values which have item 1. So if of course for every one of these values the buyer selects one of the menu items, and you're going to have exponential many of them being concentrated in a single menu entry. So there's a single menu entry that allocates a certain amount of items S star for a certain amount of price P star, and with lots of different possibilities for the values of the buyers that are choosing that thing. So of course, what that menu entry must allocate for each one of the possible values of the buyers that choose that menu entry, it must allocate basically that set of items with extremely high probability, otherwise the buyer will not be willing to buy. And then we have lots of different sets, go to the same menu entry, and of course the menu entry must satisfy each one of them, so it must satisfy their union. So on their union, you're going to be able to lose revenue, because on their union, you're still going to only accept the same price that the menu entry asks for, even though the union is now bigger. So that's like a classic combinatorial kind of thing that you can analyze like, any combinatorialist that's doing lower bounds would do, and you get the lower bound, basically. And so I don't know if I want to continue, but let me give just one other thing. With polynomial size auctions, it turns out you can get at least a constant approximation. And how would you do that? So that we can do using the following from the previous thing is that either selling everything as a bundle or selling each item separately gives you a 1/6 approximation that we've said. Now, if you're selling everything as a bundle, that's a very simple menu because you're just giving one possibility. You get everything and you pay this one. But if you're selling each item separately, there are exponentially many possibilities because you can get any subset of the different items. And the point is we want to replace allocating every possible subset with only allocating a small number of subsets with polynomial. And the question is, how can we do that? And the theorem says that you can do that. So if you're selling items separately with exponential many possibilities, the theorem says that you can actually offer only a polynomial number of possibilities and lose only an epsilon amount of revenue. And that's basically the new theorem. And now that's a little bit. So the point is, let me try to give a high-level thing. Now it's becoming more fuzzy. But the idea is you have all these items, and you're selling each one of them for a different price. And we're going to basically order them according to the price we're selling each one of the items. Now, prices that are way too low, we can just ignore. Prices that are way too high appear with small enough probability that there is no interaction with the probability of selling other items, so we handle them separately. So almost all these probabilities are within some kind of polynomial range. Now we take the polynomial range and we can split it into basically, things that are 1 plus epsilon apart in value. So now we split it into something like log n over epsilon bundles, where in each subset, the probability of buying is almost the same, or the price that you're selling is almost the same. And now the point is that in each one of them, you can do one of two things. If the probability that selling at each one of these items at that price is low enough, then you just offer to sell a single one of them at that price, because two of them will not come. Because if the total sum of probabilities is low enough, the probability that two of them together come, you can ignore. If many of them typically are sold, then you just use concentration, because you know approximately the number that's going to be sold, so you're going to sell that amount for the correct price. And because you only have a logarithmic number of bundles, then the number of combinations is exponential of that, which is polynomial, the original thing. So that's another kind of argument that you have. I expect that all of these arguments would seem natural, so at least I try to present them as very natural from a complexity point of view, even though the problem is very different. So we still have a problem, and basically with polynomial size, we know that you can get a fully polynomial time approximation scheme if you wish, get a 1 minus poly, but can you get 1 minus epsilon for every epsilon? That's still open. That's one of the interesting problems there. Yes?
So you measure complexity by menu size.
Mm-hmm.
But there could be other considerations, like how composite it is from the point of view of the buyer to decide what its best strategy is. So is there any analysis that takes either?
Yeah. Yeah, so that's an excellent question. So I would say that the interesting conceptual question is find a more reasonable model of complexity of auctions, which you can analyze on one hand, and on the other hand makes more sense, more direct sense from an economic point of view. That's a real conceptual question. Thank you. And there are some things that are in that space, but nothing clean enough combinatorially, I would say. Okay, so thank you and happy birthday, Avi.